Welcome students, welcome to Strength of Maintenance class. In the previous class we have generated shear stress distribution diagram for the rectangular section. In today's class we are going into how we will generate the shear stress distribution diagram for the circular section. So firstly, shear stress distribution diagram means if we say it is shear force diagram, so variation of shear force along the length. Bending moment diagram, so variation or point to point bending moments for the overall length of the beam. If we say stress diagram along the depth from point to point, what is the stress? When we indicate the whole in one picture, that is stress diagram. Similarly for the strain. Now we are going into generate a picture or equation of the shear stress from point to point along the depth of the beam. So we have started shear stress distribution diagrams for different sections. So yesterday also we have already came into the concept and generated rectangular sections shear stress distribution diagram. So in today's class we are going into circular sections shear stress distribution diagram. Firstly, we are considering whatever the thing we need to do, we need to consider a circular section with some diameter and having some properties. Okay? So consider a circular section of a beam. Okay, simply it is a beam member, on that we are taking a circular section, and capital R is the radius of the circular section. So let R be the radius of the section, and the shear force acting on the section is indicated as F. Okay, so simply what is the shear force that is acting at that particular section they have given, and radius of the circular section also they have given. Now we should have to consider a level EF at a distance y from the neutral axis, being as a symmetrical section, circulars, rectangulars, square, symmetrical section, we all these called as symmetrical sections. So for these symmetrical sections, at the center of the overall depth, okay, if it is a D, so at the center of the overall depth only the neutral axis lies. So half the depth means R is the indication, right? So the neutral axis location is at R level. At a distance of y from the neutral axis, I am considering a level EF. Okay, simply that is my indication for the picture. So as we already know, the formula for the shear stress is involving tau is equal to F A y bar by I into B. So the shear stress at any point is equal to F A y bar divided by I and B. Now that capital F is shearing force acting at the section, and capital A is area above which we are calculating the shear stress. As I am calculating shear stress at the level EF, okay, so above that level EF, what is the area of the portion? That portion I need to involve as A, and y bar is distance of centroid of this portion from the neutral axis. Okay, so this is A into y bar, and I is moment of inertia of the whole circular section about the neutral axis, and B is width of the beam at the level we are calculating the shear stress, and the level I am calculating the shear stress at the EF level. The value of B I need to write, that is the width of the beam, and the level we are calculating the shear stress. Okay, so I have taken a circular section with a radius R and having the section with a shear force F, and in that I am taking a level which is at a distance y from the neutral axis. So when we observe the whole picture, this may appear like this: a complete circular section with a neutral axis indication, and center they have indicated as O, and we are having a level at a distance y, and there we have got the line EF. Above that we have given the shaded portion for giving a answer, and in between this E and F we are generating a perpendicular line that we indicated as B. So this perpendicular we have plotted from O, and the corner we have indicated as B, and from 0 to F, 0 to E or 0 to F, whatever is from origin to any point on the circle, is R radius. Okay, shear stress at this level EF is given by tau is equal to FA y bar. Why into B? We have already mentioned that. And A into y bar. If you want to calculate A separately and y bar separately, then you should have to evaluate what is the area involved, and from the centroid to the neutral axis you should have to give the answer. So A and y bar individually calculated and multiplied. But here I am indicating A into y bar at a time, and that is equal to first moment of area. In the last class also we have discussed A into y bar is first moment of area above the shaded portion about neutral axis. A into y bar if it is area A and it is the distance y bar, so A into y bar is area moment about the neutral axis of the section. Okay, in this way we will calculate A into y bar, and I overall moment of inertia of the section. B is width of the beam at the level EF. As you already indicated, at the level EF I am calculating the shear stress. At the level EF I am calculating the shear stress. That's why B is width of the beam at the level EF. I is moment of inertia of the whole section, whatever is the level I am taking. Next. So, we are considering a strip of thickness dy which is at a distance y from the neutral axis, and its area is indicated as dA is that area of the strip. As this is our circular section and this is our indication, and this one is E and F, which is being located at a distance y, and in this circular portion, for evaluating the shear stress at the level EF, I am considering a small strip of thickness dy and with the area of the strip. So, when you see this, you can observe, even though it is a small strip in the circular section, being it is very thin, so I can simply consider it as a simple rectangular. See here, a simple rectangle with a width B and thickness dy. See here, as even though it is a single strip in the circular section, as dy thickness is very small, in that thickness that B is same like I am thinking, and this strip is appearing like a small rectangular section. Now, from the rectangular's point of view, okay, from the rectangular's point of view, area of the strip is equal to, that dA is equal to B into dy, width of the beam into thickness dy. And B, what is B? B is width of the beam at the level EF. Okay, so this EF is the width of the beam. And how could I calculate this value? As it one is O and this is E and F, and its measurement I have indicated as B, and we have mentioned we are dropping a perpendicular. Okay, this corner we have indicated as B. So what is this B value? That B value is equal to EF value. That EF value is equal to EB plus BF. EB plus BF. As both were same, 2 times EB. So EF is equal to 2 times EB. And how this EB will be calculated? As I know the Pythagoras theorem. So from the Pythagoras theorem I am indicating, and this measurement I know as Y. This measurement I know as R. O to R. So we are observing a simple right angle triangle with O, B and E. This one is my unknown, and this value is capital R, and this value is Y. So what is this EB's answer? How much is this EB? Generally R square is equal to EB square plus Y square. See, R square, hypotenuse or this, okay, R square is equal to EB square plus Y square. And I know I need to know EB. So that EB is equal to under root R square minus Y square. Okay, this one is EB only. So, double the EB, that is EF. So, EB is equal to under root R square minus Y square and 2 times under root R square minus Y square into dy. So, this is the length of that EF. Okay, so only width of the beam at EF only I have calculated, right? So, this one is width of the beam at the level EF. That one into thickness has given area of the strip. Now, in right angle triangle OEB, EB is equal to under root R square minus Y square. Moment of this area about the neutral axis is equal to Y times dA. So, Y into dA. Okay. So, as this is a strip, this is area A and this is NA and the perpendicular distance is Y. So, about the neutral axis, moment of inertia of this strip is equal to Y times dA. dA into Y. And that dA just now I have got the equation as 2 times under root R square minus Y square dy. So, I have replaced that dA and with the multiplication I have written 2y under root R square minus Y square and dy. Okay. So, for this Y times dA and substitution of dA has given 2 R square minus Y square dy. So, with this, with the rearrangement 2y under root R square minus Y square. What is this? That is area moment of the single strip. Area moment of a single strip which is at a distance y with an area dA. As we are having a segment like this. We are having a circular segment like this and we can indicate number of strips here, right? Discreting and integration. Here also the same thing. I need to know the complete areas. This circle, this part of the segment's area moment. Okay, A into Y I need to know. Further I have taken a single strip and further the single strip I have calculated area moment. And then number of strips may be involved in that portion where I need to calculate capital A into Y bar. So, this portions A into Y bar will be coming out from integrating this first area moment of the process strip, single strip. Now, moment of the whole shaded area. How much we have given in the picture? That moment of the whole shaded area above the level EF. Okay, about the neutral axis. So, moment of inertia of the moment of area of the whole portion, that is the shaded area above the neutral axis, is obtained by integrating the above equation between the levels Y to R. See here, it has started from the level Y and it has raised to R. The variation of dy being, dy is my variable there. See, 2y under root R square minus Y square. dy is the variable. So, the variation of y I should have to give the limits. So, the variation of y between the limits from y, from that y EF started and up to R that was ended. So, the shaded portion has started at a level y from the neutral axis to the level R from the neutral axis. So, between the limits y to R as it is, we are keeping the area moment of the single strip so that I can get the area moment of the complete shaded portion with the integration. Integral y to R under root, integral to R 2y under root R square minus Y square dy. As you already know how to give the integration for some functions, no need of thinking all the things. Only for making you easy, I have enlarged some more steps. Okay, as it is, I am keeping the function. When you observe this y square, so outside some function is there, that one is 2y. So this part's derivation is appearing like this. So that minus minus integral y to R minus of 2y. Okay, because minus y square's derivation is minus of 2y only. R square is being a constant, it will give 0 only. Okay, minus 2y under root R square minus Y square dy. Okay, if you are having f of x and f dash x, okay, function and its a derivative, what it will give? Function power n plus 1 by n plus 1. So, as I am having a function with some power, so function with some power is there, and in the derivative I am having as the multiplication function. F of x power n, something function is there. And I am having that function's derivative also in the multiplication. So that I can write as the integral output as f of x, that function, whole power of n plus 1 by n plus 1. Here also the same thing I am doing. So r square minus y square whole power of 1 by 2 I am having. R square minus y square whole power of 1 by 2 is the function I am having, and it was being multiplied with 2y. Okay, so function power something n into function's derivative. How it will come? Function power of n plus 1 by n plus 1. So r square minus y square whole power of 1 by 2 plus 1 by 1 by 2 plus 1. That I have got as 3 by 2. So r square minus y square whole power of 3 by 2 divided by 3 by 2, and I should have to indicate the limits y to r. Okay. Now substitution has given me some answer. So r square minus y square a into y bar is equal to minus. Please don't forget to keep the minus, as I need the minus inside the function, so I have kept two minuses there. Minus is not there, so but here I have kept 2 minus 2y and minus. So that minus will continue next. So a y bar is equal to this part, and I am substituting r and y. So in place of y I should have to substitute r once. In place of y I should have to substitute y once. So r square minus r square, r square minus y square. So the function with minus outside and minus here will be cancelled, and 2 by 3 r square minus y square whole power of 3 by 2 is the a into y bar of the shaded portion above level EF. So area moment of the shaded portion above the level EF. So for this whole portion's area, I have taken area into y bar. Okay, a y bar's multiplication we have got. Okay, that is this answer. And F we already got. And capital I, moment of inertia of the circular section about the neutral axis. So for that I am using the formula moment of inertia of the circular section about its own centroidal axis, that is pi d power 4 by 64. If you need it, we will substitute here. Otherwise, we will keep it in the later, and later you can substitute. And B is width of the beam at the level EF. That also we have calculated previously. Now, substituting all the terms in the equation. Substituting the value of A into y bar in the equation. So, F A into y bar by I into B. And B also I know. Width of the beam at the level EF, that is 2 times r square minus y square. So under root r square minus y square, 2 times this value is here. So substituting this b also here, and I have got this tau is equal to f by 3i r square minus y square. I didn't substitute, only answer the capital. So tau is equal to f by 3i r square minus y square. The above equation shows that what is showing? It shows that the shear stress distribution across the circular section is being parabolic. Oh, how? As the tau is the output, shear stress output, and what is the input value? Corresponding points distance from the neutral axis. As the tau is in relation with the second degree of y, that's why the shear stress distribution will be parabolic. So, like in the rectangular section, for this equation also at different points we need to calculate the shear stress. So this is my formula, and it is also indicating one more thing. As the y value is increasing, the tau automatically decreases. Same like the rectangular section, as it is there in with the minus. So y, when I am going away from the neutral axis, okay, when I am going away from the neutral axis, the shear stress decreases. Okay, this point is important, and now I am calculating at different points what is the shear stress. When y is equal to r, nothing but at the extreme top or at the extreme bottom. When I am calculating NA here, and y is at this r level. Okay, y is at r, and as it is I should have to substitute there, and I have found the shear stress at the extreme top or extreme bottom is equal to 0. As substitute in the equation, shear stress at the extreme top or extreme bottom is equal to 0 for the circular section. And at the neutral axis also I need to calculate, right? So at the neutral axis means there y distance of the neutral axis from the neutral axis. At that level only I am calculating. So y is equal to 0. Substituting the y is equal to 0, f by 3 into r square is the formula. So shear stress is being maximum as the y is becoming minimum, tau will be maximum. As it is nothing, so highest value is possible. So the tau maximum is equal to 3 by f by 3 at r square. And the tau max is equal to f by 3 r square. And we already know I is equal to moment of inertia of the circular section about the neutral axis, that is pi d power 4 by 64. And if you want to substitute pi by 64, and we know in terms of r only, right? So 2r power 4. So with this we have got 16, and 16 by 64 we have got pi r power 4 by 4. Okay, moment of inertia in terms of r. We no need to remember in terms of r and in terms of d. Only one thing you can remember. Pi d power 4 by 64. Then the diameter is equal to 2 times the radius that I have substituted, and in terms of r I have given the answer. Okay, so I we have known, and substituting this in the equation, f by 3 into pi r power 4 by 4 into r square as it is. That is equal to 4 by 3 f by pi r square. Okay, 4 by 3 f by pi r square. Okay, this is my answer. And when we are going into our basic shear stress definition, what is the basic shear stress definition? Shear stress or the average shear stress is equal to shearing force divided by shearing area. Okay, so the shearing force value by shear area is the answer. So shear force by shear area. What is the shearing area? Being a circular section, and this F is being applied on this shearing plane. Okay, so being a circular section, F is being applied on the shearing area like this. So F by pi r square is the shearing area. F by pi r square is the shearing area. So this is equal to shear stress. In general, this one is average shear stress. Basic definition of shear stress is shearing force by shearing area. That one is average shear stress only. Now, see here, F by pi r square is there, right? That's why tau maximum is equal to 4 by 3 tau average. Okay, tau maximum is equal to 4/3 tau average. So, when we indicate the picture of the shear stress distribution, a vertical line which is indicating the depth of the beam, and at the extreme top and extreme bottom I have found 0 as the shear stress. And at the neutral axis, I have found the maximum shear stress that I have indicated as tau maximum. And at any other random point, we have indicated tau value. So, this is the shear stress distribution diagram, and all the connecting points are through a smooth parabola, because the tau equation is f by 3i into r square minus y square. See here. The equation is having a second degree answer with respect to y. As the y changes, tau in a second degree answer it will change. Okay. Y is 1, tau will give 1 square's corresponding answer. Y is 2, 2 squares corresponding output it will give. So, in this way the relation of tau and y will be a parabolic relation. Now, when you see this, what is the thing happening here? So, overall depth we have indicated, average shear stress and maximum shear stress we have indicated. Okay. Next, our next section is I section. Okay, for the I section, generally for the I sections we will go into numericals. With the numericals only, it will be easy. And if an I section with an overall width B, overall depth D, and thickness of the web B, and depth of the web is B, if it is there, we will generate the shear stress equation for the I section. So generally we will go with the numericals only for the calculation. If an I section is there, generally, now next class we will go into the numerical for the I section. Okay. if these are the terms they have given, using these terms we should have to generate the stress distribution diagram for the I section. Again, I will indicate with a vertical line and indicating the corresponding points, and the neutral axis level we should have to indicate. As we already know, at the extreme fibers, shear stress is equal to 0. So, from 0 to some value it will reach. Okay, so this way it will come, and from this position it will extend in a sudden, and here also from 0 to some value it will increase and it will show some extension. Now, connecting these three and the corresponding tau maximum. So, this is the representation for the shear stress distribution for I section. When we are going into the numerical, it will be very easy for you. Only thing is, we will generate the equation, and at the top of the flange, at the bottom of flange, at top of flange, at the bottom of flange. Again, at the top of web, at the neutral axis in the web, at the bottom of the web. Again, inside, at the same position only, I will take 2 times at the same level. Below the flange, above the top of the web. Okay, so below the flange, at the same level, above the web also. At the same level only, we will calculate the shear stress. Okay. Simply, we are going into a simple comparison for bending stress and shear stress. Okay. In bending stress, what is the main formula we have used? M by I is equal to sigma by Y is equal to E by R. Okay. Then sigma is directly proportional to Y. Here, tau is equal to F A Y bar by I times B, and tau corresponding answer we have got in an inverse relation with Y square. Okay. So, with minus of Y square we are getting the answers. Due to this, what it is saying? As Y increases, sigma increases. Y increases, sigma increases. As Y increases, the corresponding tau decreases because the negative value it is offering. Right? Again, as Y is equal to 0, sigma 0. Y is maximum, sigma is maximum. So, along the depth, when Y means from the neutral axis, what is the measurement? At the Y is equal to 0, neutral axis, at the Y is equal to 0, sigma is also equal to 0. When Y is becoming Y maximum, sigma will become sigma maximum. And this will write as the stress distribution diagram. If you want, you can write bending also. Bending stress distribution diagram. So, this is the bending stress distribution diagram. If this comes as they are in a different relation, again, along the depth I have indicated, and at the neutral axis level. So, at the neutral axis level means Y is 0. As it is becoming 0, as it is becoming the least, the tau will be maximum. So, the corresponding maximum will come as the Y value is getting raised. So, I am reaching to the extreme fibers. Okay. So, as I am reaching to the extreme fibers, Y is increasing in a square with a negative, the tau will become least, and at the complete extreme fibers, it will reach to 0. Okay. So, in this way, for a general rectangular section is the bending stress distribution diagram, and shear stress distribution diagram will come. Okay. So, in the next class, we will go into the calculation of shear stress distribution diagram for an I section, and the next we will go into the T sections and triangular sections also. But one thing you should have to give the continuity towards the topic. Okay. Firstly, we have learned this thing and what it is the same with respect to y sigma is increasing. But here as y is increasing, tau is becoming less. So here at the neutral axis the bending stress is 0, but here at the neutral axis level I have got the maximum shearing stress. Okay. In the next class we will go into the next topic but with a numerical in I section for the calculation of shear stress distribution diagram along the depth of the beam. Thank you.